Right now, every galaxy you can see is racing away from us. Not some of them. All of them. And the farther away they are, the faster they're moving. This isn't science fiction. It's the most profound discovery about our universe ever made, and it completely rewrites everything we thought we knew about existence itself. In 1929, an astronomer named Edwin Hubble pointed the most powerful telescope on Earth at distant galaxies and found something that shouldn't have been possible. The light from these galaxies wasn't just shifted. It was stretched, pulled toward the red end of the spectrum in a pattern that followed one undeniable rule. Distance equals speed. A galaxy twice as far away moves twice as fast. 3 times the distance. Triple the velocity. The universe wasn't sitting still. It was expanding, and it had been expanding for billions of years. Before Hubble's discovery, humanity believed the cosmos was static and eternal. Even Einstein initially rejected the idea of an expanding universe, adding a mathematical term to his equation specifically to prevent expansion. He later called it his greatest blunder. What Hubble revealed wasn't just that space is big. It's that space itself is growing, stretching like fabric being pulled in every direction simultaneously. Galaxies aren't flying through space away from us. Space is carrying them apart. Stand outside on a clear night and look up. Every point of light you see from another galaxy is already millions of years older than it appears. The photons reaching your eyes have traveled unimaginable distances, and during that journey, the space they moved through expanded. Their wavelength stretched. By the time they arrive, they've been transformed, shifted toward the red end of the spectrum by the relentless expansion of the cosmos itself. This is cosmological redshift, and it's fundamentally different from ordinary motion. When a car drives past you, its sound shifts in pitch due to the Doppler effect. The car moves through space, compressing sound waves as it approaches and stretching them as it leaves. But galaxies aren't moving through space that way. They're embedded in space, and as space expands, it drags them along. The light they emit gets stretched not because the galaxy is racing through a void, but because the void itself is growing between us. Think about dots drawn on the surface of a balloon. As you inflate it, every dot moves away from every other dot. None of them are at the center. None of them are special. From any dot's perspective, all the others appear to be fleeing. That's our universe. We're one dot among billions, watching everything else recede, and if you could somehow teleport to any other galaxy, you'd see exactly the same thing. Every direction you looked, galaxies would be rushing away. Hubble made his discovery using the 100-inch Hooker telescope at Mount Wilson Observatory in California. At the time, it was the largest telescope ever built. He focused on objects called Cepheid variable stars, which pulse with predictable rhythms. A woman named Henrietta Swan Leavitt had discovered something remarkable about these stars back in 1908. The speed at which they pulsate directly reveals their true brightness. Measure how fast one flickers, and you know its actual luminosity. Compare that to how bright it appears from Earth, and basic physics tells you its distance. Using Cepheids, Hubble proved that fuzzy patches of light astronomers had called nebulae were actually entire galaxies far beyond the Milky Way. The universe was suddenly millions of times larger than anyone had imagined. Then he measured their light. Galaxy after galaxy showed the same pattern. Their light was redshifted, and the redshift increased with distance. The relationship was linear, precise, and undeniable. For every 3 million light-years between us, space grows by 70 kilometers every second. This number, the rate at which the universe expands, became known as the Hubble constant. It's measured in kilometers per second per megaparsec, a unit that sounds absurd but perfectly captures what's happening. A megaparsec is roughly 3.26 million light-years. So a galaxy 1 megaparsec away recedes at about 70 kilometers per second. 2 megaparsecs. 140 kilometers per second. The pattern holds across billions of light-years. But here's where things get strange. Modern measurements of the Hubble constant don't agree. Space telescopes observing Cepheid variables and exploding stars called Type Ia supernovae consistently find values between 70 and 76 kilometers per second per megaparsec. Meanwhile, measurements derived from the cosmic microwave background, the afterglow of the Big Bang itself, give values closer to 67 or 68. That gap might sound small, but in cosmology, it's enormous. The discrepancy has persisted for over a decade despite increasingly precise observations from multiple independent methods. Scientists call this the Hubble tension, and it's one of the biggest unsolved problems in physics. The difference is too large to be explained by measurement errors or observational quirks. Either something fundamental is wrong with how we measure cosmic distances, or our understanding of the universe's expansion is incomplete. Some researchers think it points toward new physics, forces, or particles we haven't discovered yet. Others believe it's a clue that dark energy, the mysterious force accelerating expansion, might not be constant over time. Recent data from the James Webb Space Telescope has intensified the debate. Webb's infrared vision can see Cepheid variables with unprecedented clarity, and its measurements closely match Hubble's earlier work. That rules out the possibility that Hubble's observations were systematically flawed. The tension remains. Yet other Webb observations measuring different types of cosmic objects have produced values closer to the cosmic microwave background predictions. The universe is giving us conflicting answers, and we don't yet know why. Understanding expansion requires grasping what space actually is. It's not a container holding galaxies like marbles in a box. Space is the fabric of reality itself, and that fabric can stretch. When we say the universe is expanding, we mean the distance between any 2 points in space increases over time. Galaxies aren't moving. The metric, the underlying geometry of spacetime, is changing. This has profound implications. Rewind the expansion backward, and the universe becomes smaller and denser. Keep going, and you reach a point roughly 13.8 billion years ago where everything we can observe was compressed into an infinitesimally small region of unimaginable density and temperature. This is the Big Bang, not an explosion in space, but the beginning of space itself. Time, matter, energy, and the laws of physics as we know them all emerged from that initial state. The expansion rate tells us the universe's age. If galaxies are moving apart at 70 kilometers per second per megaparsec, we can calculate how long it would take them to reach their current position starting from a single point. The math yields roughly 13.8 billion years, matching estimates from other methods like studying the oldest stars and analyzing the cosmic microwave background. Every approach points to the same conclusion. The universe has a finite age, and that age is written into the expansion itself. But expansion doesn't just tell us about the past. It shapes the future. For decades, astronomers assumed gravity would eventually slow the expansion. After all, every galaxy pulls on every other galaxy. That gravitational attraction should act as a brake, gradually decelerating the expansion over billions of years. Depending on how much matter the universe contained, it might slow enough to eventually reverse, collapsing back into a big crunch. Or it might expand forever, but at an ever-decreasing rate. Then in 1998, two independent teams of astronomers studying distant supernovae made a discovery that won them the Nobel Prize. They found that the universe's expansion isn't slowing down. It's speeding up. Supernovae billions of light-years away appeared dimmer than expected, which meant their host galaxies were farther away than calculations predicted. The only way that made sense was if the expansion had accelerated over time. Something was pushing galaxies apart with increasing force. Scientists named this mysterious force dark energy, and it now dominates the universe's energy budget. Roughly 70% of everything that exists is dark energy. We don't know what it is. We don't know why it exists. We only know it's real because we can see its effects. Space itself possesses an intrinsic pressure that pushes outward, counteracting gravity and driving galaxies apart at an accelerating rate. Dark energy behaves unlike anything else in physics. Normal matter and energy dilute as the universe expands. Spread the same amount of stuff across more space, and its density drops. But dark energy doesn't dilute. As space grows, more dark energy appears, maintaining constant density throughout the cosmos. It's as if the vacuum of space has weight, and that weight increases as the universe gets bigger. The more space exists, the stronger the outward push becomes. This discovery reshaped our understanding of the cosmos. 9 billion years after the Big Bang, dark energy's influence became dominant. Before that point, matter and radiation controlled the expansion rate. Gravity slowed things down. But as the universe grew larger and matter spread thinner, dark energy's constant pressure began winning. The expansion shifted from decelerating to accelerating, and it's been speeding up ever since. Recent observations hint that dark energy itself might be changing. Data from the Dark Energy Spectroscopic Instrument suggests the expansion may have accelerated faster in the past than it does now. If confirmed, this would mean dark energy isn't constant after all. It evolves over time, strengthening or weakening according to rules we don't yet understand. Such a finding would revolutionize cosmology, forcing us to rethink our most fundamental models of how the universe works. The evidence for expansion comes from multiple independent sources, each confirming the same basic picture. The pattern holds whether we look at nearby galaxies or objects billions of light-years away. Understanding expansion requires looking at how we measure it, and that measurement has become one of cosmology's most contentious debates. The problem centers on a single number called the Hubble constant, which quantifies how fast the universe expands. For every 3 million light-years of distance between us and a galaxy, space grows by about 70 kilometers every second. That rate seems straightforward until you try measuring it precisely. Then two different methods give you two different answers, and the gap between them refuses to close. One approach uses direct observations of the nearby universe. Astronomers identify special stars called Cepheid variables that pulse with predictable rhythms. The speed of these pulsations reveals the star's true brightness. Compare that intrinsic luminosity to how bright it appears from Earth, and you can calculate its distance. This technique, discovered by Henrietta Swan Leavitt in 1908, became the foundation of cosmic distance measurement. Once you know how far away a galaxy is and measure how fast it's receding, the Hubble constant emerges from simple division. The other method looks backward in time. The cosmic microwave background radiation preserves an image of the universe when it was only 380,000 years old. At that moment, the cosmos cooled enough for light to travel freely for the first time. Tiny temperature variations in this ancient glow encode information about the universe's composition and expansion rate. Mathematical models can extract the Hubble constant from these fluctuations, projecting forward to determine how fast the universe should be expanding today. Both methods are sophisticated. Both have been refined over decades. Both use completely independent observations. And they disagree by about 10%. Space telescope measurements using Cepheids and supernovae consistently yield values between 70 and 76 kilometers per second per megaparsec. Measurements derived from the cosmic microwave background give 67 to 68. That might sound like splitting hairs, but in precision cosmology, it's a chasm. The discrepancy has reached statistical significance far beyond what random chance could explain. Scientists call this the Hubble tension, and it's persisted long enough to move from curiosity to crisis. At first, researchers assumed measurement errors would resolve the problem. Improve the instruments, refine the techniques, collect more data. But the opposite happened. As measurements became more precise, the tension grew stronger. The James Webb Space Telescope recently added its infrared vision to the debate, and its observations of Cepheid variables matched Hubble's optical measurements almost perfectly. The tension wasn't an error in observation. It was real. What makes this particularly troubling is that both methods should work. The cosmic distance ladder using Cepheids and supernovae has been tested extensively. Astronomers can cross-check distances using multiple techniques, and they align consistently. The cosmic microwave background analysis rests on well-understood physics. The temperature fluctuations matched theoretical predictions with stunning precision. When two robust methods disagree this strongly, something fundamental is wrong with our understanding. Several explanations have been proposed. Maybe dark energy behaves differently than we thought. Maybe the universe's expansion history is more complicated than our models assume. Maybe unknown physics affects how light travels across cosmic distances. Each possibility opens doors to discoveries that would reshape cosmology. But none have been confirmed yet, and the tension remains unresolved. The cosmic distance ladder itself represents one of astronomy's greatest achievements. It's built in stages, with each rung calibrated against the one below. For nearby stars, we use parallax, measuring how their apparent position shifts as Earth orbits the Sun. That gives us distances to stars within a few thousand light-years. Cepheid variables extend our reach to tens of millions of light-years. Type Ia supernovae, brilliant enough to outshine entire galaxies, carry measurements billions of light-years into space. Type Ia supernovae work because they explode with remarkably consistent brightness. These events occur when a white dwarf star in a binary system pulls matter from its companion until reaching a critical mass threshold. At exactly 1.4 times the Sun's mass, the star detonates in a thermonuclear explosion. Because that mass limit never changes, every Type Ia supernova reaches approximately the same peak luminosity. Astronomers call them standard candles. Observe how bright they appear, and you immediately know their distance. This standardization isn't perfect. Small variations exist based on the composition of the exploding star and the exact dynamics of the explosion. But these variations follow predictable patterns that can be corrected for. After accounting for these effects, Type Ia supernovae become precise enough to trace the expansion history across most of cosmic time. They revealed the universe's acceleration. They mapped how expansion rates have changed over billions of years. And now they're central to the Hubble tension. The cosmic microwave background offers a completely different window into expansion. This radiation fills the entire universe uniformly, carrying information from when the cosmos was a fraction of its current size. At that early moment, matter and radiation were so tightly coupled that sound waves rippled through space. These acoustic oscillations created regions of slightly higher and lower density. When the universe became transparent, those density variations were frozen into the pattern of temperature fluctuations we observe today. The scale of these fluctuations depends on how far sound waves could travel in the first 380,000 years. That distance is determined by the universe's composition and expansion rate during that period. By measuring the angular size of the fluctuations and knowing the laws of physics that governed the early universe, cosmologists can calculate exactly how fast space was expanding then. Extrapolating forward to the present using known physics gives a prediction for today's Hubble constant. This method's strength lies in its independence from the distance ladder. It doesn't rely on Cepheids or supernovae. It doesn't depend on measuring how bright anything appears. It's pure physics applied to the earliest observable light in the universe. The precision is extraordinary. Temperature variations measured by satellites like Planck reach accuracies of millionths of a degree. Yet when this ancient light speaks, it tells a story of slower expansion than nearby supernovae reveal. Recent data has hinted that dark energy itself might not be constant. Observations from the dark energy spectroscopic instrument suggest the expansion may have accelerated more rapidly in the past than it does now. If confirmed, this would mean dark energy strengthens or weakens over cosmic time rather than maintaining steady pressure. Such behavior would require new physics beyond our current models. It might also help explain the Hubble tension by showing that simple extrapolations from the early universe don't capture the full complexity of how expansion evolved. But these findings remain tentative. The evidence isn't strong enough yet to overturn decades of cosmological theory. What's clear is that something doesn't add up. Either our measurements contain systematic errors we haven't identified, or our understanding of the universe's expansion is incomplete. Given the care that's gone into these observations, the second option seems increasingly likely. We might be glimpsing physics beyond the standard model, forces or effects that only reveal themselves across cosmic scales. Understanding what's happening requires more than better telescopes. It demands new approaches to measuring distances, alternative methods of probing dark energy, and perhaps entirely different frameworks for thinking about cosmic expansion. The Hubble tension has transformed from a measurement problem into a potential window on new physics. Whatever resolves it will almost certainly teach us something profound about how the universe works. The solutions being proposed range from subtle adjustments to wholesale revisions of cosmology. Some researchers suggest the problem lies in cosmic dust. Even tiny amounts of interstellar material between us and distant supernovae could dim their light in ways we haven't fully accounted for. If supernovae appear slightly fainter than they should, we'd calculate them as farther away, inflating our measurement of the expansion rate. But teams have spent years hunting for such systematic errors. They've cross-checked with multiple wavelengths of light. They've compared different types of standard candles. The measurements keep coming back consistent. Others point to the possibility that Type Ia supernovae themselves might not be as uniform as we thought. Perhaps supernovae in the early universe exploded slightly differently than nearby ones. Maybe their brightness depends subtly on the chemical composition of their host galaxies. These variations could introduce biases that make distant supernovae appear dimmer, again inflating our expansion rate measurements. Yet extensive studies of supernova properties haven't revealed variations large enough to explain the discrepancy. The supernovae we observe across cosmic history look remarkably similar in their light curves and spectra. Then there's the cosmic distance ladder itself. Remember, we calibrate Cepheid distances using nearby stars whose distances we know from parallax. Any error in those foundational measurements propagates upward through every rung of the ladder. If we've slightly miscalculated how far away those calibration stars are, every subsequent distance measurement shifts. But parallax measurements from the Gaia satellite have reached unprecedented precision. The foundation of the latter looks solid. What if the universe isn't expanding uniformly? Standard cosmology assumes space stretches the same way in all directions, but local variations could complicate things. Maybe we happen to live in a region where matter is slightly less dense than average. This underdense bubble would expand faster than the surrounding universe. From inside, we'd measure a higher expansion rate than the true cosmic average. The cosmic microwave background, coming from all directions equally, would give us the genuine average expansion rate. This local void hypothesis is elegant but faces problems. The void would need to be hundreds of millions of light-years across to create the observed discrepancy. Observations of galaxy distributions don't show evidence for such a massive underdense region centered on us. Some cosmologists are questioning dark energy itself. What if it's not constant? The Standard Model treats dark energy as a fixed property of space, exerting steady negative pressure. But nothing in fundamental physics demands this. Dark energy could change over time, strengthening or weakening as the universe ages. If dark energy was different in the past than it is now, simple extrapolations from the early universe would fail. The cosmic microwave background would give us one answer based on ancient conditions. Nearby supernovae would reveal current expansion driven by today's dark energy. The two measurements would naturally disagree. This idea has gained traction from recent observations. The Dark Energy Spectroscopic Instrument has been mapping millions of galaxies across cosmic history. Early results hint that dark energy might have been stronger billions of years ago. If true, the universe accelerated more rapidly in the past than current models predict. This wouldn't just resolve the Hubble tension. It would overturn decades of assumptions about cosmic evolution. But the evidence remains preliminary. The statistical significance isn't high enough to claim a discovery. More data is needed to confirm whether dark energy truly varies or if we're seeing noise in the measurements. Another possibility ventures even further from established physics. What if our understanding of gravity breaks down on cosmic scales? Einstein's general relativity has passed every test we've thrown at it, from Mercury's orbit to gravitational waves. But those tests occur in relatively strong gravitational fields. On the scale of galaxy clusters and cosmic expansion, gravity is extraordinarily weak. Perhaps modifications to general relativity become important in these regimes. Modified gravity theories could alter how space expands without invoking dark energy at all. They might naturally produce different expansion rates at different epochs or in different regions. The challenge is constructing a modified gravity theory that matches all observations. Such theories must reproduce the cosmic microwave background predictions. They need to explain galaxy rotation curves and gravitational lensing. They have to account for the large-scale structure of the universe. So far, no modified gravity theory succeeds on all fronts while also resolving the Hubble tension. The James Webb Space Telescope has brought new precision to this debate. Its infrared capabilities let it observe Cepheid variables in galaxies too distant or dusty for Hubble to measure clearly. In its first 2 years of operation, Webb collected the largest sample of distant Cepheid measurements ever assembled. Teams used 3 independent methods to calculate distances to galaxies hosting supernovae. The results aligned almost perfectly with Hubble's measurements. This confirmation is crucial. It rules out the possibility that Hubble's instruments had some undetected flaw. The tension isn't going away through better observations of nearby objects. Yet Webb has also produced puzzling results. Some analyses of its data yield expansion rates closer to the cosmic microwave background value. Different research groups using the same telescope reach different conclusions. This divergence reveals how challenging these measurements truly are. Extracting a precise expansion rate requires navigating countless potential sources of error. How do you separate a Cepheid's light from surrounding stars? How do you account for dust extinction? How do you model the star's pulsation behavior? Each choice in the analysis pipeline can shift the final answer by a few kilometers per second per megaparsec. That might sound small, but it's enough to either create or eliminate the tension. The situation has become a stress test for cosmology itself. We've built an incredibly successful model of the universe over the past century. It explains the cosmic microwave background. It predicts the abundance of light elements forged in the Big Bang. It accounts for how galaxies cluster across space. The standard model works almost everywhere we look. Yet this single measurement refuses to fit. When one piece of data contradicts an otherwise coherent picture, scientists face a choice. Discard the outlier as measurement error, or take it seriously as a sign that something's wrong with the theory. The Hubble tension has crossed the threshold where it can no longer be dismissed. Too many independent teams using different methods have found the same discrepancy. The measurements are too precise to attribute the disagreement to random noise. Something genuine is happening. Whether that something is subtle systematic error or revolutionary new physics remains the open question. Resolving it will require more than collecting additional data. We need new ways of measuring cosmic distances that bypass the traditional ladder entirely. We need better theoretical frameworks for understanding dark energy. We might need to rethink fundamental assumptions about how the universe expands. What makes this moment particularly fascinating is the convergence of observation and theory. Telescopes like Webb and DESI are delivering data with unprecedented detail. Meanwhile, theorists are exploring possibilities that would have seemed radical a decade ago. The field is alive with competing ideas, none yet proven but all worth investigating. This is science at its most dynamic, where established knowledge meets unexplained phenomena and forces us to question everything we thought we understood. One approach scientists are pursuing involves gravitational lensing. When light from a distant object passes near a massive galaxy cluster, gravity bends its path. This bending creates multiple images of the background object, each taking a slightly different route through space. Because these paths have different lengths, light traveling along them arrives at different times. When the background object is a variable source like a quasar, its brightness fluctuations appear in one image before appearing in another. By measuring this time delay and modeling the lens geometry, astronomers can determine the distance to both the lens and the background object. This method doesn't rely on Cepheids or supernovae. It bypasses the entire distance ladder. Early results from gravitational lens measurements have yielded expansion rates closer to the local universe value, adding weight to the higher numbers. But the technique has its own challenges. Modeling how mass distributes within galaxy clusters involves considerable uncertainty. Different assumptions about the lens structure can shift the calculated expansion rate. Another independent method involves measuring the cosmic microwave background in combination with observations of galaxies at different epochs. Baryon acoustic oscillations represent a subtle imprint left in the distribution of galaxies. In the early universe, sound waves traveled through the hot plasma before atoms formed. These waves created regions of slightly higher and lower density. When the universe cooled enough for atoms to form, the waves froze in place. Today, we see their signature as a characteristic scale in how galaxies cluster. This scale provides a standard ruler we can use to measure cosmic distances. Combining baryon acoustic oscillation measurements with cosmic microwave background data allows calculation of the expansion rate without using the distance ladder. These calculations typically favor the lower expansion rate, aligning with predictions from the early universe. The disagreement persists even when using completely different physical phenomena as measuring tools. The possibility that dark energy evolves over time has captured considerable attention. For decades, cosmologists treated dark energy as Einstein's cosmological constant, a fixed property of space itself. If space has an intrinsic energy density, that energy doesn't dilute as the universe expands. More space simply means more dark energy. This concept works mathematically and explains many observations. But it's not the only possibility. Dark energy could be dynamic, changing its strength as the universe ages. Some theoretical frameworks predict that the repulsive force driving acceleration could weaken or strengthen over billions of years. Testing this idea requires measuring the expansion rate at different cosmic epochs. Distant supernovae reveal how fast the universe expanded billions of years ago. Nearby objects show the current rate. If dark energy varies with time, these measurements should reveal a pattern that differs from a constant cosmological term. Data from the Dark Energy Spectroscopic Instrument has provided tantalizing hints in this direction. DESI maps the three-dimensional positions of millions of galaxies, creating the most detailed picture yet of cosmic structure. By analyzing how galaxies cluster at different distances, researchers can trace the expansion history across billions of years. Preliminary results suggest the universe might have expanded faster in the past than current models predict. The difference isn't enormous, but it's statistically significant. If confirmed, this would fundamentally alter our understanding of dark energy. Instead of being a static property of space, it would be an evolving field with its own dynamics. Such a discovery would revolutionize cosmology. It would also potentially resolve the Hubble tension. If dark energy behaves differently in the early universe compared to today, that could explain why measurements based on the cosmic microwave background diverge from local observations. Yet caution is warranted. The evidence for evolving dark energy remains preliminary. Different analysis methods applied to the same DESI data yield slightly different conclusions. Systematic errors could be masquerading as real physical effects. The history of cosmology includes several instances where early hints of revolutionary findings evaporated upon closer scrutiny. Scientists need more data and independent confirmation before declaring the cosmological constant dead. Several upcoming surveys will provide crucial tests. The Vera C. Rubin Observatory will begin operations soon, scanning the entire visible sky every few nights. It will discover countless supernovae, quasars, and variable stars, dramatically expanding the sample available for distance measurements. The Euclid Space Telescope is mapping the distribution of galaxies across cosmic time with unprecedented precision. These projects will either strengthen the case for evolving dark energy or rule it out decisively. What happens if none of these approaches resolve the tension? One radical possibility is that we fundamentally misunderstood how the universe expands. General relativity describes gravity as the curvature of spacetime. In the standard cosmological model, we assume that general relativity applies on the largest scales without modification. But what if that assumption fails? Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy. These frameworks alter Einstein's equations in subtle ways that become important only across vast distances or over billions of years. Some versions predict expansion rates that differ from general relativity's predictions. Testing modified gravity is challenging. The theories must explain not just the Hubble tension but every other observation cosmology has accumulated. They need to account for the cosmic microwave background, the formation of large-scale structure, and the behavior of gravitational waves. No modified gravity theory yet succeeds on all fronts. But the field remains active, with physicists continually refining their models. Another possibility involves reconsidering what happens in the very early universe. The theory of cosmic inflation proposes that space underwent exponential expansion during the first fraction of a second after the Big Bang. This rapid growth solved several theoretical problems and predicted patterns in the cosmic microwave background that were later confirmed. But inflation itself remains somewhat mysterious. Many different inflation models exist, each making slightly different predictions. If the details of inflation differ from what we've assumed, that could alter the predicted expansion rate we derive from the cosmic microwave background. This wouldn't mean inflation is wrong, just that we've been using the wrong version. Distinguishing between inflation models requires observations of subtle effects in the cosmic microwave background polarization. Future experiments targeting these signals might clarify which inflation model best matches reality. The stakes extend beyond abstract numbers. The Hubble constant directly determines the universe's age. A higher expansion rate means the universe is younger. A lower rate means it's older. Current estimates put the age at 13.8 billion years, with uncertainty of about 100 million years. That might seem like a huge margin of error, but it's remarkably precise given the challenge. If the local expansion rate is correct, the universe could be several hundred million years younger than we think. This creates another problem. Astronomers have identified stars that appear older than the universe itself based on the higher expansion rate. These ancient stars reside in globular clusters that formed early in cosmic history. Their ages, determined from stellar evolution models, exceed 13 billion years. If the universe is only 13.6 billion years old, these stars predate the Big Bang, which is obviously impossible. Something doesn't fit. Either the stellar age estimates are wrong, or the expansion rate is wrong, or both calculations suffer from unrecognized errors. The Hubble tension forces us to confront how science progresses when faced with contradictory evidence. We have multiple lines of reasoning, each internally consistent, yet they point toward incompatible conclusions. This is precisely the situation that drives scientific revolutions. Before Einstein, physicists struggled to reconcile Newtonian mechanics with observations of light and electromagnetism. The contradictions seemed insurmountable until relativity provided a new framework that made everything fit. Quantum mechanics emerged from similar conflicts between classical physics and atomic observations. We might be approaching another such moment. The resolution could involve subtle corrections to existing theories. Or it might require abandoning cherished assumptions and rebuilding cosmology from deeper principles. Either way, the answer will reshape our understanding of the universe in ways we can't yet imagine. The question isn't whether we'll find an answer. It's how fundamentally the answer will change everything we thought we knew. Consider what's actually at stake here. The Hubble tension represents more than a measurement discrepancy. It challenges our ability to understand physical reality through observation and mathematical models. For centuries, science has progressed by identifying contradictions, investigating them rigorously, and discovering deeper truths that resolve the conflicts. This tension might be signaling exactly that kind of moment. The cosmic microwave background offers one path forward. This radiation, filling all of space, represents light from when the universe was just 380,000 years old. Before that point, the cosmos was too hot and dense for light to travel freely. Electrons and photons scattered constantly in an opaque fog. Then the universe cooled enough for atoms to form. Light suddenly had room to move. That first free light still surrounds us, stretched by cosmic expansion into microwaves. The CMB carries extraordinarily detailed information about the early universe. temperature variations across the sky amount to only 1 part in 100,000. Yet those tiny fluctuations encode the seeds of all cosmic structure. Slightly denser regions eventually collapsed under gravity to form galaxies and galaxy clusters. The pattern of these fluctuations depends on several fundamental parameters, including the expansion rate. Scientists have measured the CMB with remarkable precision. The Planck satellite mapped temperature variations across the entire sky with unprecedented accuracy. From this data, cosmologists can work backward, calculating what the early universe must have been like to produce the observed pattern. This analysis yields a Hubble constant of about 67.4 kilometers per second per megaparsec. The number comes with very small error bars. The uncertainty is less than 1%. This isn't a rough estimate but a tightly constrained value derived from thousands of data points and sophisticated statistical analysis. The measurement technique doesn't depend on the cosmic distance ladder. It uses completely different physics. That independence should make it reliable. Yet direct measurements using Cepheid variables and type Ia supernovae consistently give 73 kilometers per second per megaparsec. The James Webb Space Telescope recently confirmed these higher values with unprecedented precision. Webb's infrared capabilities allow it to observe Cepheids in more distant galaxies than Hubble could reach. The new data doesn't resolve the tension. It strengthens the case that local measurements are correct. So we have two methods, both extremely precise, both internally consistent, giving incompatible answers. The difference might seem small, but remember what these numbers mean. The expansion rate determines how long the universe has been expanding. A higher rate means less time has passed since the Big Bang. The 7% discrepancy translates to roughly 1 billion years difference in the universe's age. That's not a trivial error. Ancient stars in globular clusters have measured ages approaching 13 billion years. If the universe is only 12.8 billion years old based on the higher expansion rate, we have stars older than the cosmos. That's impossible. Something in our understanding must be wrong. What if the issue lies in how we interpret the cosmic microwave background? The analysis assumes a specific cosmological model. We plug in equations based on general relativity, add dark matter and dark energy, then solve for parameters that best match observations. But the model contains assumptions. Perhaps one of them fails in ways we haven't recognized. Dark energy represents the biggest unknown. We know it exists because expansion is accelerating. Distant supernovae appear dimmer than they should, indicating their galaxies are farther away than predicted by simple expansion models. This requires some form of energy pushing space apart. We call it dark energy, but that's just a name for our ignorance. Standard cosmology treats dark energy as a constant property of space. Every cubic meter of vacuum contains the same amount of dark energy, unchanging across time. This assumption simplifies calculations enormously. It might also be wrong. Recent observations from the Dark Energy Spectroscopic Instrument suggest dark energy's strength may vary over cosmic history. If dark energy changes with time, predictions from the cosmic microwave background become less reliable. The CMB shows us the universe at 380,000 years old. We're extrapolating forward across 13.8 billion years. If dark energy behaves differently in the early universe compared to today, our extrapolation could give incorrect results. The measured expansion rate would reflect conditions billions of years ago, not the current rate we observe locally. This possibility excites theorists while simultaneously frustrating them. A time-varying dark energy could resolve the Hubble tension. It might also require abandoning or significantly modifying our cosmological models. The equations would become more complex, predictions less certain. We'd lose the elegant simplicity of the current framework. Another explanation involves the cosmic distance ladder itself. While Webb confirmed Cepheid measurements, the entire ladder depends on assumptions at each rung. We calibrate Cepheids using geometric distance measurements to nearby stars. Those measurements rely on parallax, the apparent shift in a star's position as Earth orbits the Sun. For very distant calibration stars, parallax angles become extremely small. Tiny systematic errors could propagate through the entire distance scale. Type Ia supernovae introduce their own complications. We treat them as standard candles with consistent peak brightness. But do they vary slightly in ways we haven't fully characterized? Environmental factors might affect the explosion. Metallicity of the progenitor star. Rotation rate of the white dwarf. Mass accretion history. Each variable could introduce subtle brightness differences that masquerade as distance errors. Cosmologists have examined these possibilities extensively. No obvious systematic error explains the full discrepancy. The measurements appear robust. Yet the possibility remains that some subtle effect, perhaps involving multiple small systematics combining in unfortunate ways, produces the apparent tension without requiring new physics. The stakes extend beyond academic interest. Understanding expansion determines the universe's ultimate fate. Will it expand forever? Slow down? Tear itself apart? The answer depends partly on the expansion rate and how it changes over time. Getting this wrong means misunderstanding the cosmos at the most fundamental level. We're also testing whether our mathematical description of reality remains valid across all scales. General relativity has passed every test thrown at it. From GPS satellites to black hole mergers, the theory works perfectly. But perhaps it breaks down in ways too subtle to detect except through precision cosmology. The Hubble tension might be the first crack in the edifice, revealing that our understanding of gravity or spacetime requires modification. This uncertainty creates an uncomfortable situation for science. We pride ourselves on objective measurement and mathematical precision. Yet here we face a straightforward question with two incompatible answers. Both can't be right. Determining which is correct, or whether both are wrong in different ways, requires observations that don't yet exist. Future experiments might break the deadlock. New measurements of the cosmic microwave background polarization could refine early universe parameters. Better distance measurements using entirely independent techniques could verify or refute the cosmic distance ladder. Studies of gravitational waves from merging black holes offer a completely different way to measure cosmic expansion, potentially providing the tiebreaker needed to resolve this crisis. Until then, we're left with competing measurements that both appear technically sound yet fundamentally contradict each other. The situation resembles standing at a crossroads where two equally trustworthy maps point in opposite directions. Do you trust the map drawn from ancient light, or the one measured step by step across cosmic distances? Both cartographers insist their methods are flawless. Both have checked their work repeatedly. Yet they cannot both be correct about where we actually stand. This impasse forces us to confront something uncomfortable. Perhaps the universe is more complex than our current models allow. Maybe dark energy evolves in ways we haven't anticipated. Or space itself behaves differently across cosmic epochs in manners our equations don't capture. The simplest explanation, that one measurement is simply wrong, becomes less tenable as both techniques improve, yet the gap persists. Consider what's actually at stake. The expansion rate doesn't just tell us how fast galaxies move apart today. It determines the universe's age. Faster expansion means less time since the Big Bang. A 73 versus 67 km per second difference translates to roughly a billion-year discrepancy in cosmic age. That's not a minor adjustment. It changes when the first stars formed, how quickly galaxies assembled, and whether our models of structure formation remain valid. The ultimate fate of everything depends on this number too. Will the universe expand forever, gradually cooling into darkness? Or could expansion slow, perhaps even reverse, ending in a catastrophic collapse? Dark energy's behavior determines which future awaits. If it remains constant, expansion continues eternally. If it strengthens, space might eventually tear apart, ripping atoms themselves into constituent particles. Should it weaken, gravity could reassert dominance, pulling everything back together. These aren't abstract philosophical questions. They're concrete predictions derived directly from the expansion rate and how it changes over time. Getting the measurement wrong means fundamentally misunderstanding reality itself. What makes this particularly fascinating is that we're watching science function exactly as it should. When observations conflict with theory, something must give. Either measurements require refinement, theories need modification, or both demand revision. The scientific process doesn't promise immediate answers. It guarantees that persistent contradictions eventually force progress, even if that progress comes slowly and painfully. Gravitational wave astronomy offers a potential way forward. When black holes or neutron stars merge, they generate ripples in spacetime itself. These waves carry information about the distance to their source encoded in their amplitude. By comparing distance measurements from gravitational waves with redshift measurements from the merger's electromagnetic counterpart, astronomers can determine the expansion rate using a completely independent method. This approach bypasses the cosmic distance ladder entirely, avoiding any systematic errors accumulated through that chain of measurements. Early gravitational wave measurements have produced expansion rate estimates consistent with both camps, sitting roughly in the middle of the disputed range. However, current uncertainties remain too large to definitively favor either value. As gravitational wave detectors improve and capture more events, this technique could provide the decisive evidence needed to resolve the tension. Within the next decade, we might finally know which measurement better reflects reality. Another promising avenue involves studying the cosmic microwave background's polarization patterns. Photons from the early universe carry not just temperature information but also directional properties revealing how they scattered off matter before reaching us. These polarization patterns depend sensitively on cosmological parameters, including the expansion rate. Next-generation CMB experiments aim to measure polarization with unprecedented precision, potentially tightening constraints enough to reveal whether the early universe measurements truly conflict with local ones or if current uncertainties have been underestimated. Meanwhile, astronomers continue refining the cosmic distance ladder itself. New parallax measurements from the Gaia Space Telescope provide ever more accurate distances to calibration stars. Studies of eclipsing binary stars offer geometric distance measurements that don't rely on uncertain assumptions about stellar physics. Water masers in distant galaxies create natural lasers whose geometry can be measured precisely, giving independent distance checks. Each improvement strengthens confidence in local measurements or reveals hidden systematic errors. The Webb telescope's confirmation of Cepheid distances represented a major milestone. It demonstrated that the local expansion rate measurement doesn't result from errors in observing these variable stars. Whatever causes the tension, it's not a simple mistake in identifying or measuring Cepheids. This narrows the possibilities considerably, forcing theorists toward more exotic explanations or deeper examinations of the assumptions underlying cosmic microwave background analysis. Some researchers now question whether we fully understand the early universe well enough to extract the expansion rate from it accurately. The CMB formed when the cosmos was just 380,000 years old. Our models of that epoch assumed certain properties about dark matter, neutrinos, and the physics of recombination. If any assumptions are slightly wrong, the derived expansion rate could be systematically biased. Testing these assumptions requires independent probes of the early universe, which is why projects studying gravitational waves from the cosmic dawn or searching for signatures of primordial black holes have gained urgency. The possibility that dark energy changes over time remains particularly intriguing. Most cosmological models treat it as a constant, essentially Einstein's cosmological constant resurrected. But nothing in fundamental physics demands this constancy. If dark energy is dynamic, varying as the universe evolves, then measurements at different epochs would naturally yield different values. The early universe measurement captures conditions billions of years ago. Local measurements reflect current conditions. Both could be correct while appearing contradictory. This scenario would require rewriting cosmological models to accommodate time-varying dark energy. The mathematics become significantly more complex. Predictions less certain. Yet the payoff would be enormous. Understanding how dark energy evolves could reveal its fundamental nature, potentially connecting it to quantum field theory or other aspects of fundamental physics. The Hubble tension might not be a crisis but an opportunity, nature's way of telling us our models are incomplete rather than wrong. As observations continue improving, the tension shows no signs of resolving itself naturally. If anything, more precise measurements have made the discrepancy more statistically significant. What began as a curious mismatch has evolved into one of cosmology's defining puzzles. Its resolution, whatever form that takes, will reshape our understanding of the universe's expansion and perhaps reveal new physics beyond our current theories. For now, we remain in this uncomfortable state of uncertainty. Two reliable-seeming measurements point in different directions. Neither can be easily dismissed. Both communities continue checking their work, searching for errors that might not exist. The universe, indifferent to our confusion, continues expanding at whatever rate it actually prefers, waiting patiently for us to figure out which measurement better captures that reality. The expanding universe isn't just moving. It's accelerating away from us in every direction simultaneously, driven by forces we can barely name and don't yet understand. Dark energy dominates 70% of everything that exists, yet we can't explain what it is or why it behaves the way it does. The Hubble tension reveals that our two best methods for measuring expansion give incompatible answers, and years of increasingly precise observations haven't resolved the discrepancy. If anything, they've made it worse. This isn't a failure of science. It's science working exactly as designed. When measurements conflict persistently despite rigorous checking, something profound is happening. Either our instruments deceive us in ways we haven't identified, or reality operates according to rules we haven't discovered. Given the care invested in these observations, the second option grows more likely with each passing year. What comes next matters enormously. Gravitational wave astronomy could provide the independent measurement needed to break the deadlock. Next-generation cosmic microwave background experiments might reveal whether our understanding of the early universe requires revision. Studies of dark energy's potential evolution across cosmic time could explain why different epochs yield different expansion rates. Each approach offers a path toward resolution, though none guarantees easy answers. The stakes reach beyond academic curiosity. Understanding expansion determines whether the universe will expand forever or eventually reverse course. It constrains when the first stars formed and how quickly structure assembled. It tests whether general relativity remains valid across cosmic scales or breaks down in subtle ways only precision cosmology can detect. Getting this wrong means fundamentally misunderstanding existence itself at the largest scales. Perhaps most remarkably, we're capable of asking these questions at all. A century ago, humanity didn't know other galaxies existed. We thought the universe was static and eternal. Now we measure its expansion rate to within a few kilometers per second across millions of light years, debate whether dark energy varies with time, and probe the cosmos when it was 380,000 years old. The precision itself is staggering. Yet precision without accuracy is meaningless. We can measure the expansion rate to extraordinary detail, but if we don't know which measurement is correct, that precision becomes a puzzle rather than an answer. The universe appears to be testing whether our mathematical descriptions of reality remain valid when pushed to their limits. So far, we haven't passed. What makes this moment particularly compelling is the convergence of observation and theory at the edge of knowledge. Telescopes deliver data with unprecedented clarity while theorists explore possibilities that would have seemed radical decades ago. The field buzzes with competing ideas, none proven but all worth investigating. Modified gravity theories. Time-varying dark energy. Systematic errors hiding in plain sight. Unknown physics emerging at cosmic scales. Each possibility opens doors to discoveries that would reshape cosmology fundamentally. The resolution won't come from a single observation or breakthrough equation. It will emerge gradually through accumulating evidence, cross-checks from independent methods, and theoretical frameworks that successfully explain what current models cannot. This process might take years or decades. The answer, when it arrives, could be relatively simple, a subtle correction to existing theory. Or it might demand abandoning cherished assumptions and rebuilding our understanding from deeper principles. Either way, we're living through a rare moment in scientific history. The kind where established knowledge meets unexplained phenomena and forces us to question everything we thought we understood. Where precision measurements reveal that something fundamental doesn't fit. Where the cosmos itself seems to be telling us that our picture of reality remains incomplete. Edwin Hubble's original discovery in 1929 showed the universe was expanding. That revelation overturned millennia of assumptions about a static cosmos. Nearly a century later, we're still grappling with what that expansion actually means and how fast it's happening. The universe keeps revealing layers of complexity we didn't anticipate. Each answer generates new questions. Each measurement exposes gaps in our understanding. This isn't frustrating. It's exhilarating. The Hubble tension represents an opportunity disguised as a crisis. Whatever resolves it will teach us something profound about how space, time, and energy actually work across the largest scales we can observe. It will either validate our current cosmological models with unprecedented confidence or force us toward new frameworks that better capture reality. The expanding universe has been racing away from us for nearly 14 billion years. It will continue expanding long after we've figured out the precise rate at which it does so. But that rate matters. It determines our cosmic origin story, constrains the universe's ultimate fate, and tests whether our mathematical description of existence remains valid when applied to the cosmos as a whole. Right now, we don't know the answer. Two equally credible measurements point in opposite directions. Both appear technically sound. Both have been checked exhaustively. Yet they cannot both be right. Determining which better reflects reality, or discovering that both are wrong in unexpected ways, requires observations and theoretical insights we don't yet possess. That uncertainty might feel uncomfortable. Science supposedly provides definitive answers through rigorous observation and mathematical analysis. Yet here we face a straightforward question with two incompatible responses. The discomfort itself is valuable. It reminds us that the universe doesn't owe us simple explanations. Reality operates according to its own rules, and our job is figuring out what those rules actually are. The cosmos has been expanding since the moment space and time began. Every galaxy we observe is moving away from us, carried along by the stretching of space itself. The farther away they are, the faster they recede. This pattern holds across billions of light-years. It reveals a universe in constant motion, driven by forces we're still learning to comprehend. That expansion shapes everything. It determines how long the universe has existed. It constrains how structure formed from the nearly uniform early cosmos. It dictates whether expansion will continue forever or eventually reverse. Understanding it means understanding the fundamental nature of space, time, and the forces that govern them across the largest scales. We're closer to that understanding than ever before. Telescopes peer deeper into space and further back in time than seemed possible just decades ago. Theoretical frameworks connect cosmic expansion to fundamental physics in ways that make testable predictions. The tools exist to resolve the Hubble tension. The observations are underway. The theoretical groundwork is being laid. What we're witnessing isn't a crisis in cosmology. It's the field pushing against the boundaries of knowledge, finding that reality is more complex than our current models allow, and rising to meet that challenge. The universe is vast and ancient, operating according to rules we're still learning to read. Each measurement brings us closer to understanding those rules. Each contradiction forces us to think more carefully about what we think we know. The expansion continues regardless of whether we understand it. Space grows by 70 kilometers per second for every 3 million light-years between objects. Or maybe 67 kilometers. Or perhaps some other value we haven't measured correctly yet. Whatever the true number, the pattern remains. Everything is moving away from everything else, accelerating outward into a future we can only partially predict. That's the universe we inhabit. Expanding, accelerating, mysterious. Built on forces we can measure but don't fully comprehend. Governed by equations we can write but might need to revise. Vast beyond imagining yet knowable through careful observation and rigorous thinking. The Hubble tension is just one thread in that larger tapestry, but pulling on it might unravel assumptions we didn't know we were making. And that's exactly how progress happens. Not through confirming what we already believe, but through discovering where our understanding breaks down and building something better from the pieces.